A as in apocalyptic.
It's still a little smoky yet, isn't it?
Are they like burning extra debris? Because I thought they got it 100% contained.
So contained doesn't mean it's out in the middle. It just means it's not expanding.
Oh, okay.
And so it could be smoldering 100%
right.
and have 100% containment.
Right. So you got a lot of stuff that's still burning in the middle, and then they are doing some back burns still as well. Stuff that is partially burned but not burned enough for it to be considered safe in the future. You know, stuff that basically now is just debris. They are still doing some back burns on some of that stuff, as far as I understand.
Yeah, the way people were talking about it, they were acting like the fire was completely out. So.
Yeah, definitely not. Although once we got through that, once it was 100% contained in the basin, and then we got through that windstorm that we had, then they were, at the end of the evacuation, they're pretty sure there's not going to be any issues with structures in the basin. That doesn't mean it's going to be out. Basically, it'll keep burning until we get rain or snow.
What if you do a quality study on, let's just say like cognition of LTCC students at like 100 AQI, 150, 200?
That'd be interesting. Because it definitely affects how you feel as far as your throat and your lungs and everything. So it'd be interesting to see if there was any sort of mental aspect to it. I would think, if nothing else, just because it's affecting your sleep.
Sure.
Yeah, waking up tired and tasting like an ashtray. You've got to put a damper on things.
I don't know what that was the food my wife was cooking. That's the smoke inhalation.
I didn't feel any like effects of the smoke in the way that people are saying they felt it. They say they felt it in like runny noses and sore throat. The smell of it just makes me nauseous, but I haven't felt like sore throat or anything.
I mainly get it as, by the end of the day, especially if I'm spending any time outside, my mouth feels gritty.
Yeah.
And right now it's also hard to tell. I do have a bit of a sore throat, but it's hard to tell how much of that is being back in the classroom after summer break and how much is smoke, because I always get a sore throat the first 2 weeks of class.
Like talking?
Yeah,
Sharing?
talking and projecting and
sharing knowledge.
Yeah,
I wonder
exactly.
what so one of the problems right now with the kids in school is a lot of these guys, especially with not just this, but the ragweed counter stuff, allergies, sensitivities, sniffy nose, any kind of congestion, they're sent home from school and they gotta be tested. And the nurse will tell you, hey, we don't know if you tested negative for COVID, but you still need to do this and that, and
it's a lot more hoops to jump through than a normal school year.
yeah.
I only had about half of the normal school year with the kids before COVID hit, so I don't really know what a full normal school year would feel like anyway.
Right. So.
But it's definitely, and plus we're starting to reintroduce new after-school activities for my kids now too. So Valence has her first dance class at 4:15 today.
Oh,
So that'll be fun. I fear for the dance instructor that she gets full bad news. I think Valence takes it out on me and Laura more than other people. Like, she's really good with her baseball coach about listening and not taking out frustration on him.
Yeah.
But I fear for her coaches in the future.
Yeah, there's that.
All right, so we'll go ahead and get started. A lot of you are still sort of worrying is the wrong word, but still trying to wrap your head around the idea of these resonance structures being hybrid orbitals. And it really is very similar to the way that we mix together s orbitals and p orbitals to make sp3 orbitals. We did that mathematically by taking these different functions and sort of adding them up to get something that was in the middle, that was not like either of the pieces, but it was made up of two pieces. These resonance structures are really, really similar to that. It's a way to mix together these different molecules. It's one level removed. So if you have atomic orbitals are basically, what's this blue one? atomic orbitals are just your basic s orbital, p orbital, d orbital. And when you mix those together, you get, stuff like sp3 orbitals that are hybridized orbitals. And we do that because that allows us to make more bonds and get more. If we have more covalent bonds, that means that we have more valences that can be filled. So overall, it winds up lowering energy. We take these atomic orbitals and mix them together. So S, E, E, etc. If you take these new hybridized orbitals, though, and you let them overlap with other hybridized orbitals, you get molecular orbitals. So it's the same process, we're just doing it again. And now these molecular orbitals are the actual bonding orbitals. So the molecular orbitals are the ones that look like sigma bonds and pi bonds. And then if you take these molecular orbitals and then mix them together one more time, you get resonance structures. And so the individual resonance structures look like all the molecular orbitals put together. But when you take those different resonance structures and mix them together, that's when you get these resonance structures, these that are hybrid pieces put together. So it really is, it's the same logic and the same math, frankly, that we did up here to go from atomic orbitals to hybrid orbitals. We're just doing it again, now that we have multiple possible resonance structures, we're doing it again. And once again, it's because it's going to lower your overall energy of the system by mixing these things together. And so if you think of them as just being mathematical functions, you could do, we've done this before where it said something like, f of x plus g of x, and gives you a new function when you add them together. And then if you took that new function and added it to a third function, so it's just, we're layering these things on top of each other. And it's still a matter of debate whether or not that is really what happens, because it's not like nature's out there with a pen and a paper saying, oh, we're going to take this orbital, mix it with that orbital. Or this is just the mathematical way we have of representing what happens to the orbitals when you put them together. But we do know that these resonance structures and molecular orbitals are what these orbitals look like, as far as where you're going to find electrons and where, the strength of the bonds and everything. So it's our best way of describing it, and really we just don't have the firmware to really truly process what's happening in quantum systems. Our brains don't work that way. That's not how we've evolved, because it's never been an advantage evolutionarily to understand quantum mechanics. Right, so with that in mind, I know it's a stretch, but really just understanding that that when we do these hybridized orbitals, what we get is really the sum of them mixed together, and it's not any one of those resonance structures at any given time. And got a question about revisiting molecular formulas. So, I'm teaching the Gen Chem students are learning about protons, neutrons, and electrons today. So if you remember learning about protons, neutrons, and electrons, it was a matter of just, you go to the periodic table, you count up your positive charges and your negative charges and your mass number, and it's the same process basically every time. Molecular formulas are sort of the OChem equivalent of atomic structure, counting protons, neutrons, and electrons, except we're counting carbons, hydrogens, and oxygens. Right, so it's just a matter of going through, totaling up all of your carbons, all of your hydrogens, all of your oxygens and nitrogens, or whatever else happens to be in there, and just summing it up. And when I say molecular formulas, we're not looking at any sort of condensed structure. We're not trying to convey structure at all. It's just sheer, this many carbons, this many hydrogens, this many nitrogens. right? So for the purpose of getting a molecular weight, basically, is the most common reason why we would do this. So if we're going through here and doing molecular formula, that's odd. Doesn't let me draw on the. You have to do that. There we go. So I'm gonna circle in red all of the carbons. Remember, the end of each line is either a carbon or it's whatever we explicitly label. Oh, that was good. Apparently Control Z does not work with annotations. So we've got 6 carbons here, we've got 2 here, got another 1, 2, 3 that are part of this ring up here, 4, 5, 6, 7, 8. So 2, and then another 3 over here. So we just total all those up. We got our total number of carbons. So 6 and 5 is 11, plus another 5 is 16. So it's C16. That's all we're looking for, right?
Where were you on the quiz? That's too easy. So I did the cyclopentane, we did a cyclopentane, and then is that a cyclo, I guess, hexane with the oxygen in the middle?
So that's going to have a whole different name because it's got an oxygen as part of the ring structure.
Okay.
So it's what we call a heterocycle because not all the things are the same. So, but yeah, we're not going to name that.
I was doing the individual and then trying to add it all together, and in the end it was just way too confusing, but I think I still pull off half a point. But that's, thank you for clarifying.
And the main thing, the trickiest part with these is always going to be counting your hydrogens because they're not explicitly laid out, right? Carbons, oxygens, nitrogens, those are all pretty straightforward. Hydrogens, it's going to be a matter of count to 4 but not 5 for every carbon. Right, so 1, 2, only 2 hydrogens on the benzene ring. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21.
Gotcha.
Right, so make sure that every carbon has 4 bonds, and beyond that, it's just totaling everything up. So it's going to be C16, H21, 1 nitrogen, and 2 oxygens. And typically, I'm not going to be picky about the order of these. But if it's organic compound, normally we'd start with the carbons and hydrogens, and then list the rest of them in order of electronegativity. But again, it's not. I'm not going to be picky about the order that you write these in. Right, so when it comes to counting hybridization, we're getting pretty good at that. I think most of you are getting the hang of doing the hybridization. For the carbons, it's pretty straightforward, right? Everything's sp3, and then every pi bond that a carbon has, you take away one of those p's. So sp3, because there's no pi bond. sp3, sp2, 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 sp2. sp3, 3, sp3, 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 sp2, sp3, sp3. SPs are fairly uncommon. It's pretty uncommon to have either a triple bond or 2 double bonds on the same carbon. There's a couple of really common examples of that. Carbon monoxide is one, acetylene is one, carbon dioxide is one, but other than those, we don't see that often. sp2s are way more common, especially because benzene rings are really stable. Counting lone pairs is sort of like counting hydrogens, right? So you're just going through everything. We know none of the carbons has a lone pair unless it's got a negative charge. So we're going through everything that's not a carbon or a hydrogen and making sure it's got a total of 8 electrons. So this oxygen has 2 bonds, so it's got 2 lone pairs to go along with that. Nitrogen has 3 bonds, it's 1 lone pair. This oxygen also has 2 lone pairs. You guys, I think pretty much everybody got that one right. Delocalized lone pairs is a little trickier. Delocalized means that they can participate in another resonance structure. And so the delocalized lone pairs are going to basically be anything that's adjacent to a pi bond. It's in that allylic position. So this oxygen has 2 lone pairs, one of which can enter into a resonance structure with this benzene ring. Right, and that resonance structure is going to look a little bit weird. I'm just going to draw that bottom part of this molecule, not the whole thing. But if you have a lone pair on this oxygen, the resonance structure could look like, okay, this oxygen could donate that lone pair, and then you would need to make room by moving the pi bond over. So we wind up adding 2 formal charges, so it's not going to be that, the major contributor. But we didn't break any full valences to do that, at least, right? So it's not an insignificant contributor. So that anytime you've got a lone pair that's adjacent to a pi bond, there's going to be a resonance structure there, and that means that lone pair is delocalized. Because it's not stuck just being a lone pair by itself. The caveat with that is that out of the 2 lone pairs on this oxygen, only 1 can be delocalized. You can't have both of these lone pairs participating in resonance at the same time. So even though there are 2 lone pairs on that oxygen, one's going to be delocalized, and its orbital is going to look like a pi bond. The other one is going to be stuck in its normal spot, and it's going to be more or less just like a lone pair that's, let me think how to phrase that. It's going to look like a sigma bond or like an sp3 orbital, where it's got that balloon shape that's stuck in one place. Right, so if we're counting the number of delocalized lone pairs, there's one of them that's on this oxygen down here. Does this oxygen have a delocalized lone pair? Randy, you're shaking your head. Why not?
Because they can't go anywhere.
They can't go anywhere. There's already a pi bond here, right? If there's already a pi bond, then the lone pair can't also resonate where that pi bond is. So basically, every atom that can go through resonance that has either a pi bond or a lone pair can only contribute at most 1 pair of electrons to the resonance structures. So this oxygen already has a pi bond, so its lone pairs are localized. They're stuck where they are. This nitrogen, on the other hand, has a lone pair adjacent to a pi bond. So this nitrogen's lone pair is delocalized. How many of you guys have had cell bio or any form of biochem? So peptide bonds are a really common example of this in biology. And a peptide bond is what you get when 2 amino acids react together, right? And you wind up with that functional group that in OChem we call it an amide. And I realize also I've never officially defined these. Anytime I want to say there's some more stuff there but we don't care about it, or there might be more stuff there but we don't care about it, we usually represent it with an R group. R just means more carbons, maybe it's a hydrogen. Usually it means more carbons, but we don't care what they are. So in this case, I'm interested in talking about this functional group, so there are other carbons there, but I'm just going to ignore them. Say they're there and move on. This functional group, all 3 of these heavy atoms are planar. They're all sp2, despite the fact this nitrogen looks like it should be sp3. But it's planar it's sp2 because this nitrogen's lone pair can resonate with this pi bond. You get a resonance structure that would look like this. Again, we didn't break any full valences to do that. We added clonal charges, but we didn't break any valences. So this is still a significant resonance contributor. And that means that this nitrogen has to be shaped. The Vesper geometry in the hybridization has to be in a way that lets that lone pair turn into a pi bond. So there's a reason why I didn't ask about the hybridization on the nitrogens, on the nitrogen or the oxygen here, because on paper it looks like they should be sp3. But realistically, these two that have those delocalized lone pair are actually going to behave more like they're sp2. All right, so for total number of delocalized lone pairs, there would only be two. 2 out of your 5 lone pairs are delocalized here. And that does wind up affecting the shape of these things, and that affects things all the way down like protein folding, right? If your peptide bonds have to be, all 3 of those atoms have to be planar relative to each other, that's going to affect how much freedom of rotation you have with those polypeptide chains. So alpha helices that you get when proteins fold up and you wind up with these protein chains forming these spiral structures, they form every 7 amino acids you can have. It repeats, it completes one turn of the spiral. And that's because that's what's going to allow you to, with the restriction that these things have to be planar, that's how you can line it up so that one oxygen's partial negative is lined up pointing towards another amino acid's hydrogen from the nitrogen, because this is going to be a partial positive. So you wind up with these polar bonds making this overall alpha helix shape, and it's constrained, and it has to happen every X number of amino acids at most, because we're stuck with these all being planar, with these being sp2. Right, so these things wind up building on themselves, and it's not entirely obvious when you take biochemistry why we care about hybridization until we start breaking it down and looking at the individual atoms in a protein, which is really, really granular, right? Which is really zoomed in. I thought this was an interesting question. I was wondering how resonance responds to environments. I understand it's kind of an average probability thing, but are people at healthy blood pH more likely to have a different major contributor of an organic compound than people with alkaline or acidic blood pH? So if you're just looking at one isolated environment, then you're really going to be looking at everything's going to have more or less the same resonance contributors. But you can absolutely affect how stable various resonance contributors are by changing the environment. If you put it into a more acidic environment, then you can wind up protonating certain lone pairs. And if those lone pairs are protonated, they can no longer be delocalized. So if we go back, that's the wrong keyboard. If we go back here, this nitrogens, amines in general, are fairly basic. They're pretty easy to protonate. We're going to talk a lot about acid-base chemistry today. But as soon as you protonate this and you make it an NH2 with a positive charge, well, now all of a sudden that lone pair can no longer be part of resonance structure, right? Because you can't break a sigma bond to make a resonance structure. So you can absolutely influence which resonance structures are possible for major contributors based on pH. In fact, that's one of the reasons, like we mentioned the other day, why acetic acid is acidic, is because as soon as you get rid of that proton, that opens up a possibility of making a resonance structure that you didn't have before. Right, so Absolutely, and we can favor, even without full-on protonating things, you put things with the right solvent, you can stabilize certain resonance structures. For instance, a really common molecule, how did I get this blue pen again? I tried. If you put this molecule in a non-polar solvent, it looks like this. If you put it in a really polar solvent, its resonance structure is going to look like moving both of those over, and you wind up with a negative charge and a positive charge. Normally, this is not a really significant contributor, right? Because we had to break a valence shell to do that. But in a really polar environment, where you can form favorable interactions between positive charges and the solvent molecules around them, this becomes more likely. So you can tweak those probabilities. You know, this might have been the major contributor at like 99.9% of the time in a non-polar solvent, and maybe it's now 95 to 5 in a polar solvent. So we can emphasize certain things by changing solvents, by changing polarity, by changing acidity and pH. All right, and we've already gone over this, but just to reiterate, we're not going to have a ratio of resonance forms among the population of molecules. Each molecule itself will have molecular orbitals that look like the average of the possible resonance structures. So it's not like we could go in there with molecular tweezers and grab one molecule and say, hey, I got this resonance structure this time, right? It's not like you really have them flickering back and forth. It really is that average out sort of sum of the possibilities. And then somebody asked if there's a mathematical way to predict how many resonance structures you will see. The real answer for that, the one that the mathematicians want me to give, is yes. You can absolutely do a bunch of math to predict how many possibilities there are. The problem is that you then have to go through and remove a bunch of probabilities if they break, or possibilities if they break any of our rules. So from a practical standpoint, not really. Because if you think about every single pi bond, you just look at benzene. If we look at every pi bond has 3 possibilities, right? You could have a pi bond going from carbon 1 to carbon 2. That pi bond could also be in the position where it goes carbon 1 to carbon 6. Or it could exist as a lone pair. So that really, for every carbon that has a pi bond, there are 3 possible states. But some of those are not possible all at the same time, right? So we could go through and say, well, that's 6 carbons, they each have 3 possibilities. 3 to the 6 would be the number of possible resonance structures we could have. Well, not really, because some of them are going to wind up giving 10 electrons to a carbon. We can't do that. So we would then have to go through and subtract off the ones that break our chemistry rules, or the ones that are insignificant contributors because we wind up making 2 empty valences when we started with everything full. Right, so yes, mathematically you could go through and predict how many possibilities there are. The thing is, most of those possibilities are going to be garbage. So we really need to use those rules we've gone through and made as our best way of determining, where do I stop writing resonance structures? And basically, if you're introducing 2 unfavorable things at the same time, then that's almost always going to be insignificant. Like if we're adding formal charges and we're breaking a big full valence up, that we're going to say that's going to be insignificant for the most part. So with that in mind, we're basically sort of doing glorified guess and check. It's a little bit like balancing reactions. Larry Green will tell you when you take linear algebra that you can use linear algebra to balance your chemistry reactions, but that's more work than just doing guess and check. Same for resonance structures. You can do the math, find all the possibilities, but it's more work than it's worth for the most part. So we'll just get better at seeing what these possibilities are. And even I will still miss a resonance structure, especially if it's an insignificant resonance structure or a minor contributor. There will be times when we're doing examples where I might not write all of the resonance structures, and you guys will have to catch me on that. Because it's just one of those things that you start to see it more and more, but it's still easy to miss something occasionally. All right. This was actually a question from one of my Gen Chem students that is worth getting into in this class because we're doing all this super abstract stuff right now. You know, how the heck does hybridization and resonance structures actually matter in the real world? Why would somebody actually study this originally when they had no idea if it was ever going to be applicable or not? And there are lots of good examples in science history of it was not always immediately obvious how game-changing it might be, but where people that were doing research that had, on paper, had no practical applications, turned out to be something that would change the world. So the number one example I go to is James Maxwell. And actually, if you guys remember in Gen Chem reading sections of Demon Haunted World by Carl Sagan, that's one about skepticism and pseudoscience. He also has a chapter in that book, I believe it's called Maxwell and the Nerds, that is basically about why we should fund peer research. It was written in the 80s, so it was a dig at Reagan at the time for cutting the NSF budget and the NASA budget, and basically saying we don't need money in these things anymore because they're not practical. James Maxwell was one who came up with Maxwell's equations of electrodynamics, which was basically, he's the person who linked electricity and magnetism. Up until Maxwell, they didn't realize that magnetism and electricity were two sides of the same coin. And James Maxwell was mostly a mathematician. He did a little bit of physics, but he mostly did math. And he realized that these functions that describe magnetic fields and electrical fields were really, really similar, and that if he added a term, he could combine them. Which, again, doesn't really seem all that helpful. Cool, electricity and magnetism are now the same force. That's awesome. That's okay, we understand the world better now. Except that it almost immediately turned into radio transmitters. Anything that communicates data wirelessly is based on Maxwell's electrodynamic equations. Because the idea that this magnetic field and this electrical field were linked together allowed them to start embedding information on radio waves. So, and that's not something that if the Queen of England, so Maxwell was Scottish, so if the Queen of England at the time had said, all right, all you British scientists, I want you to find a way for me to talk in my palace and have my voice heard in every house in the kingdom, that would have gone nowhere, right? But it came, that result, the ability to have radio transmissions and cheap radio receivers was a direct result of something that had no applicable value at first. Right? So you can't always dictate what applications you want science to progress into. Another good one is quantum. Quantum seems really removed from everything, right? Especially when you look at the really basic level of atomic orbitals and look at, you know, Einstein and Bohr and Max Planck and all those guys. But semiconductors are based around quantum mechanics. You can't have semiconductors if you don't have quantum mechanics. If you don't have semiconductors, then you don't have computers or LEDs or CRTs and TVs and so on down the line, right? So all this stuff that seems like it has no practical value or is a waste of money winds up having world-changing implications down the line, and not always in a predictable way. And the people that are approving these grants are going through, they're looking for practical applications to approve grants a lot of the time. But they can't always predict where the biggest breakthroughs are going to come from or where their applications will be. So that's why it's important to continue funding pure research, even if it has no practical applications on paper. Because we just don't. We might not know where those applications are yet. it's funny how much of Demon Haunted World is, still really applicable. It was written in 1984. I think it was actually 84. That'd be too poetic. 86 or so. And still, a lot of the same arguments are still being hashed out. Hannah?
I just kind of wanted to add on to this. I hear some people say that NASA doesn't deserve funding because we should focus on the problems that we have on Earth. And I used to kind of think in a similar way, but NASA research actually helps us get a bigger picture on issues on Earth. And Mark Rober actually made a pretty good video about why NASA is important. And one of the examples that really stuck with me was a device that they sent into space that helped scan for like weather patterns and the soil conditions, so that people knew which crop to plant and which would survive, and that helped with world hunger, that helped with like so many things, predicting drought and
we're so dependent. That question was originally brought up in with regard to NASA and space travel and research in space, and it's absolutely true that we're so dependent on satellite data in our everyday life in ways that don't even fully realize. And none of that happens unless we're funding NASA, because NASA's the one going out there. It's basically we're using public funds to subsidize research that companies can then turn around and use to make money, which seems like that's just not fair. Why don't we just make the companies do their own research? But companies don't exist like that, right? Companies exist to make money where they know they can make money, not to go out and do research in some new weird fundamental science. That's how a company goes out of business, unless you're Elon Musk, or if you could get into Google and Amazon are doing stuff like that in the computer science realm. They're already so big they can afford to lose money on things. If they take a gamble and they hit 1 out of 20, they can still survive. The average startup can't do that, and that's where most of the creative thinking happens. So we kind of need to keep funding, using public funds to fund pure research in order to keep. Industry will take care of the applications. Industry will find the applications. But if they don't have the pure research behind it, then we're limited where we can go with it. All right, this was the other quiz question, the only one that wasn't that same molecule. We want to draw the resonance structures here. We can start by just moving one pi bond one spot at a time, right? We've got an empty spot in a carbon atom. So we can move this pi bond over, which puts a positive charge here. So our first resonance structure is going to look like this. Right, and then we have another pi bond adjacent to a positive charge. So then we can move those electrons over. Now we moved our positive charge one more spot. We can do that again, right? Puts positive charge here, and pretty much everybody got those ones. The last one, though, is a delocalized lone pair. Remember that oxygen has lone pairs on it, right? One of which can contribute to a resonance structure. Which now puts the positive charge on the oxygen. Up until this very last one, all the others, including the one we started with, are relatively the same amount of contribution, right? They all have the same number of incomplete octets. They all have the same number of formal charges. Formal charge can't get any closer to 0 for any of these. However, this one is going to be our major contributor. Even though it puts a positive charge on an oxygen, everything has a full valence once you do that. Once everything has a full valence, that's our number one priority when it comes to which of these resonance structures is most stable. And this is always one everybody forgets because it's not standard notation to draw out your lone pairs, right? So it's easy to forget those lone pairs are there. Remember that they're there, and then remember that that allows you, that these carbocations with a positive charge means that incomplete valence. And so by definition, less stable than if we can have all full valences. Any other questions on the quiz? On this one, or any of the others?
Yeah, that was mostly tricky because oxygen was just super electronegative. But I really felt that wouldn't contribute, but I didn't think to like draw it out and be like, oh no, everything's
Right, and that's,
which
so,
I would have played.
yeah, you guys have had enough chemistry at this point, you have some, what we call chemical intuition. You guys at this point have some idea of what makes sense when you draw a structure and what doesn't. And this one does seem like it would be less stable because of that positive charge on an oxygen. That's because you guys don't have any experience with carbocations yet. When you see a carbocation, your first thought should be incomplete valence. And then that starts making more sense because the incomplete valence matters more than a positive charge being on an oxygen. Right, so we'll continue to work to develop that chemical intuition, and one of the big switchovers that you guys have to do is recognizing that a carbocation means incomplete valence.
Sean, what was the progression on that? You went from top left to bottom left to right to top right?
Yes.
Okay.
Right, and this one was coming straight from
Yeah.
one strong. All right, we're going to do some review in a different area, one that doesn't necessarily seem like it's that closely related to a lot of orbital stuff. But one that winds up mattering a lot in organic chemistry in terms of lab techniques, and that's acids and bases. And so this slide probably looks familiar. One of the first things we do when you get taught about acids and bases, we say, well, there's 3 definitions. Here are these 3 definitions. And we talk about how they really are all talking about the same thing, just from a different perspective. And for the most part, once again, we're going to talk in acids in OChem about Bronsted-Lowry acids. So an Arrhenius acid is anything that when you put it in water increases your number of H+ ions. Now we understand that that's not actually H+ ions, it's really hydronium ions, so H3O+. But Arrhenius didn't know that back before, in the 1800s. They didn't understand that entirely yet. Interestingly, Sponte Arrhenius, in addition to having a cool name, Sponte Arrhenius, I think there's probably an umlaut in there somewhere, Scandinavian. He was actually the first person who ran the numbers in the 1800s to show that the Industrial Revolution was going to cause climate change. He actually, went through and said, well, we're pumping this much CO2 into the atmosphere. CO2 is a greenhouse gas. Actually, maybe we can affect the environment of the entire planet. Because up to that point, everything was so isolated that it was like, well, the planet is such a big system, nothing humans could do could possibly make a difference. Until Svante Arrhenius went through and did the math and said, no, actually, no, it could. And he was Swedish, I believe. And he actually thought initially that was going to be a good thing for humanity because it meant things didn't get as cold. But he was Swedish. They're worried about things being too cold, apparently. But this is, it really does, it's a good history of science lesson because that was in the 1880s. 100 years later, petroleum companies are still trying to bury their own internal research about climate change. And climate change is not a new phenomenon. It's not something that scientists are just figuring out about. We're just figuring out the full extent, and our models are getting better. But it's been known that was happening since a guy whose name is in every general chemistry textbook in existence. So he had the most basic definition, not basic, most simple, easiest to measure. Arrhenius acids, anything when you dissolve it in water, lowers the pH, is the other way of phrasing it. Right? It's the way that they actually measured it at the time. Bronsted and Lowry came along and said, well, from a molecular point of view, it makes more sense to think about an acid as being anything that can give up an H+, a hydrogen ion, which, again, we usually call a proton for the sake of simplicity. Just a reminder, we're not changing the nuclear structure of any of these. When we say a proton donor, that means we're just moving an H+ from one thing to another. Right, so no nuclei are being changed. Just hydrogen is just one proton and one electron, right? And so if it's a hydrogen ion, it doesn't even have the electron. So it's just an H+, so we just call it a proton. And then Lewis acids we'll get into. We actually will spend some time talking about Lewis acids in this class, not today probably. But a Lewis acid is the other side of the same coin here. If a Bronsted-Lowry acid is a proton donor, a Lewis acid is an electron acceptor. We wind up seeing that happens a lot in terms of catalyzing organic reactions because you can do something like put iron ions into a solution and they're going to attract electron density towards themselves because they have a positive charge. And that makes them acidic. And it means that when you put iron ions into a water solution, the pH drops. Because they wind up attracting the oxygens in the water molecules towards themselves so strongly that it makes the water molecules themselves more likely to give up an H+. So these are all tied together. We're mostly going to approach it from this level for now. And really the only common Lewis acids when we're going to be talking about Lewis acids and when that's actually going to matter, it's mainly going to be metal ions. When you put metal ions into solution, you get these Lewis acids that can catalyze certain organic reactions. And bases are always just the flip side. So an Arrhenius base means something when you dissolve it in water increases the concentration of hydroxide ions floating around or raises the pH. A Bronsted-Lowry base is the proton acceptor. A Lewis base is the electron donor. The way I keep the Lewis acids and bases straight is I have Bronsted-Lowry acid and base pretty much memorized. That's our normal way of thinking about it, and I always just remember that Lewis acids and bases are flipped. So if it's a Bronsted-Lowry acid, it's a proton donor. If it's a Lewis base, it's an electron acceptor. You basically flip both of those things, flip proton to electron, flip donor to acceptor. It's sort of like multiplying everything by -1 twice. You get the same thing, right? You turn proton to electron, you turn acceptor to donor. All right. This slide is mainly just reminding you of what a conjugate base is. So a conjugate base is what's left over after an acid gives up a proton. right? And so the other way you can think about it is it's the conjugate base would be the base if the reaction went backwards. If the reaction went backwards, the conjugate base is what would be accepting the proton. But the other way of thinking about this is I kind of, once you get used to this terminology, you think about conjugate acid-base pairs. Base pairs. Because every Bronsted-Lowry acid has a unique conjugate base that goes with it. So they're always going to wind up being paired together. Acetic acid will always have acetate as its conjugate base. So remember, acetic acid, CH3, CO2 with an H. If that acts as an acid and you lose that hydrogen, you get CH3, CO2 with a negative charge. That's the acid, that's the conjugate base, and they're always going to be paired up together. The conjugate base will always go with the same acid. So thinking about them as acid-base pairs can be helpful. Right? Just a reminder that the conjugate base is just the deprotonated form of the acid. Deprotonated meaning it's lost its H+, it's lost a proton. Right? So that's another term that we will use to describe things a lot is protonated versus deprotonated. Protonated just means it's got the H+ attached to it. Deprotonated means it doesn't have the H+ attached to it. So every lone pair can be protonated. Every lone pair, you could take an H+ and stick it on that lone pair and have it stick there. Some things are easier to protonate than others, and some things are easier to deprotonate and take something that has a hydrogen and remove that hydrogen ion to leave a negative charge behind. Right, so but these conjugate acid-base pairs are always going to be, the acid of the pair is going to be the protonated form. The base of the acid-base pair is going to be the deprotonated form of the same molecule. Right, so we're not talking about an acid-base reaction at this point specifically where we can say this is the acid and here's the base. We're talking about here's the acid and here's the acid missing its proton. So it's before and after. All right, so again, more Gen Chem slides that I pillaged and threw in here. Conjugate, this is actually good enough for your language classes. Conjugate means to join together in Latin. So in other words, they're attached. Your conjugate acid-base pair will always be matched up by definition. Whatever the acid is in a acid-base reaction will always turn into the same conjugate base, and your base will always turn into its own conjugate acid. So whether something is gaining or losing a proton depends on whether it's the acid and the base over here. Once you know what's the acid and what's the base, the conjugate acid and base are always going to be the same for the reactants. So when water acts as a base, it always makes hydronium as its conjugate acid. When water acts as an acid, it's going to make a conjugate base. What's the conjugate base going to be? Yeah, if you take an H+ away here, you get hydroxide. So water's conjugate base is hydroxide. Water's conjugate acid is hydronium. All right, we're always just talking about do we protonate or deprotonate. What does that do to your overall formula or a specific functional group? All right, there's some practice with organic molecules. You guys have done lots of practice with this with inorganic stuff, with polyatomic ions and things like that. Same logic applies to organic molecules though. So let's take our break and come back at 5 after. And we'll go through these two and label acid base, conjugate acid, conjugate base for these organic molecules. 5 after.
I'd like to give another cool chemistry question.
Not at all.
Cool. We got dinged by the city for having our cyanuric acid levels that are too high. And the solution is you completely drain all the water, start over from fresh. You're supposed to have like 30 ppm because it acts like a stabilizer for the chlorine for the UV light.
Mm-hmm.
But if you use stabilized chlorine, it's just a matter of time before you accumulate levels that are over 100, which are a little like unacceptable.
Of the cyanuric acid?
Yeah. So I was just wondering, like, what seems like it should be possible to come up with some kind of additive or something that you could introduce into the pool water that would change that into something else, or maybe tear it apart in a certain way, or get it to precipitate out or something.
I think the last one is probably the most likely.
Yeah.
There's probably a way that you could add something to make it precipitate out.
Yeah.
The problem is you have to run a cost-benefit analysis because it might be cheaper, especially if you consider that it might be some iron is really common for getting things to precipitate out because it's not very soluble. But iron is colored, right? And it precipitates out with a lot of stuff. So you might have to dump a lot of iron in, and it's going to color the water yellowish,
Right.
which is not going to be pleasant. So people couldn't be in it at the same time. And you might have to use a lot of it. It might be cheaper to drain it and refill it and just let it slowly build back up to where it was. I mean, what's the timeline that it took to build up to those levels?
We drained everything, started from zero back in like July or something, and within like 2 weeks or 4 weeks, we were up and running. But that's when there's real high usage and you're having to introduce a lot of the chlorine. We're using the stabilized trichlor tablets, so they have like 60% cyanuric acid in them. So you could go to like a liquid chlorine, which is, you could potentially go through like 2 or 3 gallons of liquid chlorine in one day just to maintain if there's like heavy usage and stuff like that. So it's just not real practical. Plus you're like pouring buckets of chlorine. It doesn't look real good.
So yeah, it could be that because of where we are and the fact that our UV is more intense than most places,
Yeah.
and we also have more evaporation than most places.
Yeah.
It could be that you need to use a different solid chlorine tablet that has a lower cyanuric acid.
We actually switched over to bromine.
Okay. So bromine, you have to be, as long as you're checking your levels, that should work.
Yeah.
Usually we use bromine for hot tubs and chlorine for pools, especially if your pools are cooler because it's the difference in temperature.
Right.
The higher temperature means bromine is just as, in a hot tub means bromine in a hot tub is just as effective at killing bacteria.
Yeah.
But if your pool is warm, say warmer than 80 degrees, then that chlorine might be too reactive, and that might be why you're going through it so fast.
Yeah.
And bromine might be a better option for that, and if it also lowers your cyanuric acid levels.
Yeah, and the problem that I run into with the bromine is that it's not super soluble in the form of the tablets that we have, so they like erode really slowly relative to like the demand that's there. So we're supposed to have a bad check valve in the erosion feeder, so I'm going to change that out and see if that helps with the feeding process. But yeah, the feeder with the bromine wasn't keeping up, so I was having to manually add chlorine just to make sure that everything's sanitary. But the whole goal is to move away from chlorine
and just use bromine and get all these feeders set up in a way where it's adequate no matter what the humidity and stuff like that. I was just thinking like that might be a cool product if you could come up with something that's like practical and doesn't have that many problems. If you could eliminate cyanuric acid, that's like, I mean, there's nothing on the market today that would be like that.
So, yeah, so the bromine should need it less than chlorine. And the other option is to go to a saltwater pool, rather than chlorine.
I haven't done any investigation on that.
So that's sort of the new route that a lot of like gyms and high-end like resorts and stuff are going to, because it's way easier on people's skin. Chlorine and bromine is pretty nasty on your skin, especially over time. So a lot of pools are going to saltwater systems, but I don't know if it's as easy as just switching over, or if you would have to get a whole new like pump system or anything like that.
I wonder how you feel about measuring like the amount of salt in there.
It's pretty similar. You can look at, so I don't know if this is the way they do it. For my head initially goes to, I know you can measure total organic dissolved solids, right? And if you looked at the density of the water and you remove total organic solids that you could measure from that, what's left over should be salts.
Maybe you could look at like specific gravity or something.
Yeah.
See how buoyant it is.
That's what I would, because specific gravity is density, right?
Yeah.
Just in different units.
Yeah.
So you could definitely do that. As far as the bromine tablets dissolving too slow, that part of that's going to be because it's in a pool, not a hot tub.
Right.
So what you might want to do for the pool is crush them up.
Yeah.
More surface area means it'll dissolve faster, and then you could do something like put them in the filter basket or something, put them under the filter basket so they're not at the bottom of the pool.
Yeah. Yeah, we've got like this inline feeder tube thing.
Okay.
That's got like 2 or 3 different connections, like before and after 90, so there's like a difference in water pressure that makes it want to flow through there or whatever. But yeah, it just seemed like that might be something cool to come up with if you could get it to like precipitate out and then you just scoop that shit up in a skimmer or something like that would be cool.
Yeah. The problem is if it's going to make it precipitate if you're going to use metal ions to do that, it's going to most likely be more dense than water, and so it's not going to sit on the top. It's going to collect on the bottom and the sides. You're going to wind up with a lot of scale, like lime scale, similar to that happening on the sides. But maybe you could do something about, instead of precipitating it out as an ionic compound, maybe do it with some soap. Do a surfactant that is, because that's a polar molecule.
Yeah.
But it's also it's also organic, right? So it should have some favorable interactions with soap as well.
Oh.
So that might be where you could get it to collect at the top and then skim it off. So maybe once a week or something, you dump some soap in, agitate it, let it collect at the top, and then skim off the top. And you probably are going to remove a fair bit of the cyanuric acid with that as well. And the more we're going to talk about acids and bases, the more basic the water is, the better that will work. Because that cyanuric acid is going to be more protonated. More protonated means less soluble in water. And so I don't think you probably want to change the pH of the whole pool just to make so you can remove the cyanuric acid.
Right.
But it's something that you certainly could.
I think it'd be fun to do it on like a really small scale, like maybe with a half a liter of water or something.
Yeah, you could do
a
a test run like that. So cyanuric acid, its pKa is pretty high. So it'd be unlikely to be able to get it fully protonated, but it's got 3 acidic protons, right? If I'm remembering what the structure was properly.
Yeah, I think that's the way I remember it too.
Yeah. So the first one of these, you're not going to be able to get to stay there. The most basic proton was a negative pKa. So one of these is always going to stay protonated. One of them is always going to be deprotonated. The third one is going to fluctuate depending on the conditions. doesn't give us the middle one.
Well, that's interesting that those are telling you the different protons have different pKa as well.
Yeah, that's a pretty wide swing. They always are going to be different. Like phosphoric acid's got 3 protons, right?
Oh, yes.
H3PO4. And the first one has a pKa like 2, and the second one is like 7, and the last one is like 10.
I know that like they're
So like they're always going to be different because once you start accumulating a negative charge, it's harder to pull a proton away, right? It's because you have a more negative charge now.
Yeah, maybe I'll try to set up a little experiment and then I'll just ask you, you know,
Yeah,
maybe
by
try
all
it or
means.
something.
By all means.
Can't do reptiles, we can do reptiles.
I like them.
No. It's that primal brain that just, that fight or flight is just, I don't like it.
A lot of people like play drinks on each other at work, and it's usually like popping out of places and scaring. I always go to the ground. Like instead of running, I just like go to the ground and like turtle and shelter in place. I'm like, God, I would be the worst in like an actual danger situation because I'm just like turtle.
So,
I'm not running. I'm staying and planting and getting close to the ground.
So when I do my movement therapy, the first intake, we go through like 10 series, once a week
Yeah.
for 10 weeks. And the first thing that you hone into is their orientation. Are they ground oriented or are they sky oriented?
I am ground, for
Usually
sure.
one of the two.
Yeah, and I usually study like sitting on the floor. Like I think better closer to the floor. It's my go-to when I feel threatened. I go to the floor. Yeah, I'm very ground oriented.
And ideally, it's a mix of both, right? Not family down
Yeah,
orientation and not just be like kind of Mike Tyson ground oriented T-Rex. That's nice, like.
yeah. I mean, I'm like, yeah, I guess supposed to be because my posture is pretty bad too. I'm really forward ground. I just want to be close to the ground at all times.
Something to the.
It's my friend. I like it.
Flight or turtle?
Not a turtle. 100%.
I usually end up like thinking, oh, I'm gonna fight, but then I'm like, no, don't punch that person, walk, and so I end up in like this kind of like.
Yeah, no, I didn't realize it until people kept scaring me and like catching it on video, and I always go to the bush.
Yeah, I look like I'm freaked out because I walked into a cobweb or something.
It's better, it's at least you're trying to do something, right? It's better.
I'm like trying to do everything all at once, so I just flail.
All right, so let's bring it back here a little bit. This is also going to apply to today's lab, is we're actually going to do some interesting things with solubility in pH. Because if we look at this, so if we look at these compounds here, we've got a benzene ring with an OH. This is a molecule called phenol. And while we're not doing nomenclature yet, I will just stress that anything that ends in OL, OL is the suffix that means that you have an alcohol. Alcohol has the OL at the end of it as well, and alcohol is an OH group. So in this case, phenol, if you know what you're looking for, you start seeing a lot of organic prefixes and suffixes showing up in medications as well, which you might expect, but they don't always follow our rules for naming, but the parts will usually be there. So OL means it's got an alcohol. The other term for a benzene ring is a phenyl ring, PHENYL. So if you take a phenyl ring and you add an alcohol on it, you get phenol. So the pronunciation gets a little tricky to specify, right? Phenyl is pronounced like the root vegetable. Phenol is this molecule here. Right? And so you want to emphasize the OL when you have phenol to avoid confusion there. And to make things more complicated, phenyl doesn't taste anything like a phenyl ring or phenol. Phenol has its own odor to it, but it's not anything like the vegetable. So phenol here, we can remove an H plus. So we'll go from its protonated state to its deprotonated state. So that means out of these, which is the acid, out of hydroxide or phenol? Phenol. It's donating its H plus, and it's protonating the base. The other way we could phrase it, right? It's giving the base an H plus. So the acid would be phenol, the base would be hydroxide. The conjugate base of phenol, and this makes it really obvious it's the same molecule missing an H plus, right? Organic compounds, it's really easy to see that. It's a little harder sometimes in inorganic stuff, like phosphoric acid versus dihydrogen phosphate. Sometimes it's harder to see it's the same molecule. This makes it really easy to see it's the exact same molecule missing a hydrogen. Right, and that means that our conjugate acid would be water. And we'll see this a lot in OChem, that basically none of these acid-base reactions are going to be irreversible. Pretty much every organic acid and base is a weak acid, weak base, which means it's an equilibrium reaction, and if you change things over here, you can get it to go backwards. Right, so again, that's one of the reasons why this acid-base pair winds up being such an important concept, is because if you take phenol and you put it into basic conditions, you can deprotonate it. If you turn around and take this and put it in acidic conditions, you can protonate it again. So you can deprotonate and protonate kind of at will just by changing the pH. Which of these forms would dissolve better in water? Protonated or deprotonated for the phenol? Deprotonated. Charges dissolve better in polar solvents than polar compounds, right? Especially considering this polar compound, while being technically polar, it's not that polar. It's got a lot of non-polar section for one alcohol group. And this is more of a lab tidbit than something that would show up in lecture that often, but usually the cutoff for where we consider an alcohol to be soluble in water is about 4 carbons for every OH group. If it's got more carbons, more than 4 carbons per alcohol, then it doesn't dissolve in water. So phenol, we would not expect the phenol to dissolve in water very well, if at all. It's got 6 carbons that are all, and all this is all non-polar, and one little section of the molecule that's polar. However, phenolate, which is phenol minus its hydrogen, the conjugate base of phenol, does dissolve in water, because it's got a full-on negative charge, which is even more polar and even more strongly attracted to the polar water molecules now. Right, so by changing pH, not only can we change whether things are protonated or deprotonated, we can change whether they'll dissolve in water or not. How about down here? We've got a ketone, and we've got an amine with a negative charge, which we call an amide. It's not an amide group, because that's a carbonyl next to a nitrogen. It's a deprotonated amine, or an amine anion. Which of these is going to be the acid, and which of them is going to be the base? One on the left is giving up a proton, right? It's going from being neutral to being negatively charged. Versus the amine is going from being negatively charged to neutral. And if we look at where the lone pairs are, we can see what's happening on the amine at least. So the amine initially has 2 lone pairs. We take an H plus from that other molecule, basically you wind up with a lone pair from one of the lone pairs from the nitrogen, it just reaches out and grabs one of the hydrogens to give you the protonated amine, or the neutral amine, and the deprotonated ketone. So we'll talk in this class about how to determine which proton is more likely to be pulled off, because there's a lot of options on this right here, right? And same for knowing where we're likely to protonate something. But in order for something to be a base, it has to have a lone pair. Basically, you have to have space for an H plus to come in and attach. If you have something that has no lone pairs, it can't be a base. It's already full up with hydrogens. There's no place to put another hydrogen. So amines are nitrogens are the most common bases that we see, but oxygens can act as a base as well, especially if they're starting out negatively charged. And then usually the more common acids are going to be hydrogens that are attached to something that's more electronegative. So OH groups are more common. This is kind of an uncommon base. In fact, this is a really, really strong base. Sorry, uncommon acid. This is a really, really strong base that you have to put it with in order to deprotonate a carbon. Carbons are almost never going to get deprotonated unless you have a really strong base. And this is actually a really common one that gets used to get this reaction to happen. And I didn't prep for that lecture, so I don't remember what that base is called off the top of my head. Dibol. No? DIPA. Diisopropylamine is this molecule here. Yes.
Okay, so just to double check understanding, so the base gets protonated and the acid gets deprotonated.
Correct.
Okay.
Which makes this the conjugate base and this the conjugate acid, because this is the protonated form of the base. And the protonated form can always be deprotonated if we change the conditions. Right, so the conjugate acid is the same molecule as the base, just with the extra H plus added. The conjugate acid is the protonated base. Just an example of carboxylic acid groups acting as an acid when you put them in aqueous environments. And so it basically fits both of these definitions. When you put an acid into a water, you're going to increase H3O plus concentration by having water act as the base. So when you add an acid to water, you make the solution more acidic. You lower the pH by forcing water to act as a base. All right, quick recap of equilibrium. What's the first rule of equilibrium? Close. Close. Products over reactants. What's the second rule of equilibrium? Products over reactants. So you were going with the right reference there, actually. No, products over reactants. Products over reactants. Always, your equilibrium constant is always products over reactants. And the nice thing about OChem and acid-base equilibria is that in general, we don't even usually have to worry about any funny coefficients and exponents, because almost always in OChem and in acid-base chemistry, we're dealing with things that are one-to-one. Our balanced reactions are almost always going to be one-to-one, because you're always going to be looking at, okay, well, this acid has one proton to give. This base will accept one proton. So if all of your coefficients wind up being one, then your equilibrium constant, you don't get any coefficients up as the exponents or anything like that. So if this is our definition of a weak acid reaction, so remember K sub A was for a weak acid reacting with water. So Ka is always going to be for the same type of reaction. It's always whatever acid molecule we're talking about reacting with water to form hydronium and the conjugate base. All right, so the conjugate base of acetic acid is acetate. So we wind up with the conjugate base, which a lot of times, to make it general, rather than write the formula or the structure, we just write the deprotonated form. So in HA is just a generic acid. It's written that way because the H is the proton that it can lose. So in that case, if this is our generic acid, then our conjugate base would just be A minus, the deprotonated form of that acid. So the equation for Ka is always concentration of the conjugate base times concentration of hydronium over concentration of the acid times concentration of water. What's the third rule of equilibrium? I didn't teach you guys equilibrium, so you guys haven't heard these from me like that before. No liquids or solids. Right, liquids and solids have a constant concentration, so we leave them off of this. That means water doesn't show up. So really, our expression for Ka is conjugate base concentration times hydronium concentration over the concentration of the acid, the protonated form. We're just going to take this and do a little bit of algebra with it to get to the buffer equation. You guys remember using the buffer equation? Maybe a little bit. The buffer equation is the one that has pKa. So P, just like pH, just means it's a mathematical operator that says take the negative log of something. So pKa means you're taking the negative log of Ka. And that means we can say the negative log of this whole term, right? This is where it starts looking a little bit funny because logs make simplifying everything weird, right? The laws of logs are a pain when it comes to simplifying things. Well, one of the laws of logs that you'll see when this shows up all over the place in science is that if something is multiplied together inside the log, that means you can separate it out as being a sum. So, in other words, we can say pKa equals negative log of A minus over HA concentrations plus the negative log of H3O plus. All I did was, because this is multiplied, we can separate it out and turn it into a plus. And since there was a negative sign on the outside, we're still going to have a negative sign here. Why is this helpful? Well, we have a definition for the negative log of hydronium concentration, right? That's our definition of pH. So that allows us to rewrite this as pKa equals pH minus log of A minus over HA. And I think that might be a typo. This is also called the Henderson-Hasselbalch equation. make sure that I didn't miss a negative sign there. Oh, it's because it's rearranged to be pH. Okay. So this is one way to write it. The more common way to get rid of that negative sign is just to move log over, and you get an equation that says pH equals pKa plus this other log term. Right, and so we will continually come back to that as a way. We don't use it for making buffers in this class the way we use it in biology or in Gen Chem. pH equals pKa plus log A minus over HA. We use this to actually estimate this ratio for a given pH. If you know what the pH of a system is, and you know that you've got a certain acid that has a certain Ka value, we can look at the difference between the pH and pKa and say, very generally, what is this ratio? How much of my acid is protonated versus deprotonated? Which means we can predict whether it's going to be soluble in water or not, based on the pH. All right, so a reminder that of what we went through the definition of Ka, it's just an equilibrium constant. A lot of times though we wind up with tables of pKa's, because pKa gets, you can then compare pKa's to pH directly and have one-to-one. So a lot of times we will have tables that are not Ka values, or they're pKa values. Right, and this is helpful. It's not as helpful if we're actually trying to solve an ice table like Gen Chem. If we're trying to solve an ice table like Gen Chem, we probably want to take these pKa's and turn them back into regular Ka's so that we can get our concentrations that way. But it's really helpful in terms of being able to look at this, because the more negative a pKa, the more acidic something is. So the lower Ka, the lower the pKa, the more acidic something is, because remember we have that negative term on the log. So the lower pKa is, the bigger Ka was before we took the negative log of it. So sulfuric acid having a pKa of -9 tells us that the Ka value for sulfuric acid is like 10 something times 10 to the 9. So really pretty big Ka value, right? Favors the products really heavily. But for a lot of these other organic compounds, we're in the realm that's more like what we would see in a solution or in the body, in physiological pH. Acetic acid has a pKa of 4.75. This is a diketone, it's not a beta, this is a beta diketone. We actually can deprotonate that carbon. It's got a pKa of around 9. Right, so this is just a generic table just to show that we have a range of pKa's here. We get some pretty high pKa's too, which means it's really, really hard to deprotonate some of these things. You can deprotonate acetylene, but it's got a pKa of 25, which means in order to deprotonate acetylene, you have to get your pH close to 25, which is really, really acidic, or really, really basic. All right, so in general, low pKa is a strong acid, high pKa is a strong conjugate base. Right, so we wouldn't say, in the same token, we'd say acetylene is really bad at being deprotonated because its pKa is so high. So it's a really weak acid. On the flip side, the deprotonated form is going to be a really, really strong base. If you were able to deprotonate acetylene, that resulting acetylide ion winds up being really, really strong base, because it's really unstable in its deprotonated form. The conjugate base is a really strong base because it's so unstable, which is why it's so hard to deprotonate it in the first place. It's such a bad acid because the conjugate base is such a strong base. Right? Two sides to the same coin, just different frame of reference. Are we talking about it as an acid or as a base? So the flip side of that one is if it's a really strong acid, like hydrochloric acid has a pKa of -7, that means chloride is a really bad base. It's a really weak base. Right? Strong acid, and that's again with that conjugate acid-base pairing, they're always paired up. And we're always going to be talking about them. Is this the deprotonated form or the protonated form? Are we talking about an acid or a base here? But they're always going to be related. And so if you have a table like this, it really tells you everything about acid-base strength, right? A lot of times they won't even show the conjugate base because once you know what the conjugate base is, you don't even need to write it. You just need the structure for the acid. The conjugate base is just the deprotonated form. All right, so you can't read this table that well, but I'll help walk through this. Having a general table like this that has a bunch of different functional groups as well and their relative acidities also allows us to do things like find the most acidic proton on this molecule. Because there's a lot of hydrogens on this molecule, right? They're not equally acidic. The different functional groups and the different orbitals and the different, we call it the molecular environment. The different environment of that proton is going to affect how acidic it is. So if we're looking at these, the most acidic protons are usually attached to electronegative elements. We see that if we look at this chart too. So the most acidic protons are usually going to be attached to a conjugate acid group, if we have one. In the conjugate acid group, when you've got a carbon-oxygen double bond with an OH attached to the same carbon, they have pKa's usually between 4 and 6, depending on what's attached to it, what the R group is. If we don't have one of those, we can still look at other functional groups on this molecule. Say, okay, well, we have an ether. If ether doesn't have a proton, it can give up, right? So that's not going to be very acidic. We have an OH and an NH. So if we come over here and we look, okay, well, I've got some alcohols. These OHs have pKa's around 16 to 18. Nitrogens, to deprotonate a nitrogen, nitrogens are already good bases. They're already really good at getting protonated. So the flip side, they should be really bad at getting deprotonated. So to take a neutral nitrogen and turn it to a negative charge is really hard. So our alcohols all have pKa's around 16 to 18 region. Ammonia is down here at 38. And remember, this is a log scale, right? So a difference of 20 in pKa units means it's 10 to the 20th times harder to deprotonate a nitrogen than an oxygen. Right? If you made an equilibrium reaction of an alcohol with a deprotonated amine, we could predict the Ka value, and it's going to be something like 10 to the 20th, favoring stealing the proton from the alcohol and giving it to the deprotonated amine. Right, so, and again, we'll get practice with that later. So, but if we wanted to look at this, well, that oxygen doesn't have a proton, so it's not that one. You can deprotonate carbons, but it's really hard to do. Oxygens are a lot easier, alcohols are a lot easier to deprotonate than nitrogen. So this is our most acidic proton. And so it sort of just has a hierarchy. You know, carboxylic acids are your most acidic, then follow that with alcohol hydrogens, and then follow that with amines, follow that with carbon hydrogens. You know, there are other factors that can change this. For instance, one of the ones that I pointed out was this: if you have two ketones with one carbon in between them, that actually makes that a fairly acidic proton. It's pretty easy to deprotonate that carbon. It's because it has these two other functional groups next to it that are going to affect the orbitals. If you deprotonate this to get this negative charge in between these two, there's actually now all of a sudden there's some resonance that can happen, right? Having pi bonds adjacent to a negative charge means that you can have resonance structures. So having resonance structures on the conjugate base means it's easier to deprotonate. Which is also why phenol is a lot easier to deprotonate than any of the other alcohols. Phenol has a pH around, or pKa around 10, but ethanol and isopropyl alcohol and tert-butyl alcohol all have pKa's 16 to 18. Because the deprotonated form, the conjugate base, has resonance that can happen. All right. So I think at this point you're with me on some of the general concepts. Strong base versus a weak base. If I asked you to actually come up with a Ka value for a specific reaction using that table, you might struggle a bit, but that's okay. Here's where it gets a little bit abstract because it's going to have layers of logic that we have to go through. We've done all the layers, but putting them all together and being consistent the whole way through can be tricky. Here's our buffer equation, the Henderson-Hasselbalch equation. pH equals pKa plus log of the conjugate base over the acid. When the pH equals the pKa, that means this whole term has to be 0, right? If pH is equal to pKa. And how do you get log of something to be 0? What's log of what gives you 0? Log of 1 gives you 0, right? So we need this ratio to be 1 for this whole term to turn to 0, right? So what that means is if pH equals pKa, you must have both of these in equal amounts. That's the only way that ratio turns into 1, right? So by definition of equilibrium and pH, we can say that when the pH equals pKa, the acid is 50% ionized, or deprotonated, or you have equal amounts of the protonated and deprotonated form. Okay, cool, right? What does that give us? Well, all of a sudden, that makes the pKa's much more useful, especially, not necessarily intuitively, but in your mentally, if you're just trying to do some back of the envelope estimation or something in your head. It allows us to look at a table like this with all these pKa's and say, okay, well, what's the pH that I need to get to in order to protonate something or deprotonate it? Physiological pH, neutral pH is around 7, right? So if I want to have an equal amount of acetic acid and acetate in a solution, I need to get down my pH to be 4.75. So in other words, if I start from a neutral solution, I need to make it more acidic in order to protonate the conjugate base. So if our pH does not equal pKa, the other side of this is it tells us whether we're more likely to find, if we pick a molecule at random with our molecular tweezers, is it the protonated form or the deprotonated form? In other words, what is the ratio at a given pH of the deprotonated to the protonated? So if your pH is above your pKa, that means that this whole number has to be positive, right? Log of what gives a positive number? It's got to be the top half of this has to be bigger than the bottom half in order for the pH to be above the pKa. And so if you're more basic than the pKa, you have to have more of the deprotonated form around. Which makes sense, right? That's the conjugate base. If you're more basic than the pKa, you've got more of the conjugate base. If you're more acidic than the pKa, that means this side of the equation has to be bigger, of the fraction has to be bigger. So if you're more acidic than the pKa, you have more of the protonated form. So let's try applying this. We have the ionization of benzoic acid in water. Benzoic acid is just a benzene ring with an acid group on it. If we put that with water, you get an equilibrium reaction where we're going to deprotonate the benzoic acid and protonate the water. So we wind up making benzoate. And H3O plus. So that's our ionization reaction. Just like from Gen Chem, except now we're drawing structures instead of just using formulas. If we have a solution that has a pH of 7.2 and pKa of benzoic acid is 4.2, is it more protonated or deprotonated? I'll write the equation back up here again. pH equals pKa plus log of A minus over HA.
Deprotonated
Deprotonated, why?
because the pKa is less than the pH, which means that we would have more of the deprotonated than the protonated.
Correct. So and the way that my mind works when it comes to working the logic through with this is that I always go back to, I know it's 50-50 when these two are equal. 7.2 is more basic than 4.2, right? So if it was even at 4.2 and then I made it more basic, that means I'm pulling more protons away from stuff to make it more basic, right? So if your pH is higher than your pKa, you have less of the protonated form around and more of the deprotonated form. Okay, so more basic favors the conjugate base. More acidic favors the conjugate acid. And I always use the pKa as my reference point because that's where it's even. We can actually solve this. We can actually get a number for what the ratio is. Really roughly though, remembering that it's going to be a log base 10 scale, 3 pH units means that this ratio is going to be 10 to the 3. In other words, going 3 pH units above the pKa means it favors the deprotonated form 1,000 to 1. And we didn't even have to get that basic, and all of a sudden we've got 1,000 to 1 favoring the deprotonated form of this acid. And so this is what we're going to do in lab today, is basically play with the pH to make things either more soluble in water or less soluble in water. If they're less soluble in water, they're usually more soluble in an organic solvent. So by changing the pH, we can change whether this compound will dissolve in water or nonpolar solids, which means we can do things like an extraction. And so you're going to be doing a lot of what are called acid-base extractions in lab today, which basically you have a solution that has some nonpolar molecule in it. If you mix that solution with a basic aqueous solution, you can deprotonate this molecule. And when you deprotonate it, all of a sudden you favor it dissolving in water instead of the inorganic base, instead of the nonpolar solution. Right, so we tweak the solubility by changing the pH, which means we can control which layer of a two-layer system our molecule is in. All right, so we'll talk a little bit more about the factors that affect pKa. And we already mentioned this a little bit, nitrogen versus oxygen versus carbon. If we want to look at what's more acidic, it's going to be the elements that are most stable with a negative charge are usually going to be the most acidic. Because if they're more stable with a negative charge, that means that you're not really making it that unstable of a system by deprotonating it. So oxygens are easier to deprotonate than nitrogens, and nitrogens are easier to deprotonate than carbons. Because we're always going to be looking at, for acidity, we're looking at what's the stability of the acid we're starting with. But a lot of times we're looking at what's the stability of the deprotonated form. Is the deprotonated form really stable? Because if it is, that's going to make it even easier to take a proton away. So electronegativity, would we expect or weaker base than an alcohol? So we just said that alcohols are better acids than amines. So the flip side is that we would expect an amine to be a better base than an alcohol. It's easier to protonate this than it is to protonate an OH group. And it comes back to electronegativity, right? Oxygens like sharing less than the nitrogens. So it's easier to protonate a nitrogen than an oxygen. Because remember, when you protonate things, think of that Lewis acid definition, Lewis base definition is about electron donor versus acceptor. If something's going to be a base, that means it has to share electrons more than it normally would. Nitrogen does that better than oxygen. All right, would we expect most of the amines to be protonated or unprotonated at a pH equals to 7? And pay no attention to those pKa numbers because I believe I grabbed the wrong pKa value for the alcohol there. This is the pKa value for deprotonating the alcohol, not protonating it. So would we expect most of if we're at a pH of 7, what form is the amine going to be in? Most of it.
The acid for the protonated.
Yeah, so if we look at the two forms here, you've got the neutral nitrogen versus the protonated form. So our possibilities are versus the protonated form. If a pH of 9.4 means that these are equal in concentrations, if we go more acidic, that means more H pluses around, right? So more acidic means you favor the conjugate acid. So we would expect more of the amines to be protonated if we're at a pH that's lower than the pKa. Which of these is going to be more soluble in water?
Protonated.
Yes. And so this is where it gets tricky because we can't make a generalization that says protonated means more soluble. The generalization we can make is charged is more soluble in water. But some functional groups are charged when they're protonated, and some functional groups are charged when they're deprotonated. Think about the carboxylic acids, right? Carboxylic acids, when they're protonated, they're neutral, and when they're deprotonated, they're charged. So for carboxylic acids, they're more soluble when they're in their deprotonated form, but amines are more soluble in water in their protonated form. And so this is what I mean about there's layers you have to walk your way through. When we're talking about we want something to be more soluble in water, we want it charged. Then you have to say, okay, charged for this functional group means deprotonated. Deprotonated means more acidic than the pKa. Right, so the pKa is always going to be our dividing line between protonated and deprotonated, but you have to walk your logic back to get from, I want it to be soluble here, what do I do to the pH? Right, through those other steps along the way. A couple other things that affect pKa, the size of an atom. If you have larger anions, you can spread extra electrons over a larger volume, which means hydroxide is less stable than what is that molecule? It's not a sulfide ion, I don't think. There's a name for that ion in particular that I'm coming up with. Hydrogen sulfide works. But I can't remember what the name for that one is, actually. So that means that dihydrogen sulfide is more acidic than water because this ion, this conjugate base, is more stable than the hydroxide. Okay, we're always looking at the stability of the conjugate base is generally the way we approach estimating pKa. And last, since I know I'm running out of time, is resonance. Resonance affects pKa because if your conjugate base, your deprotonated form, has more resonance than when it was protonated, then it's easier to take that hydrogen off. And conversely, if protonating something means you lose resonance, that's going to be harder to protonate. It's harder to protonate some nitrogens compared to others because sometimes protonating that lone pair means it's now stuck where it is. It can't participate in resonance anymore. Right, so looking at the stability of what you have versus what you're making when you protonate or deprotonate something is going to affect the pKa values. All right, last thought. Which of these protons is going to be more acidic? Let's do this one first. The nitrogen or the oxygen? Oxygen is more acidic, the nitrogen would be more basic. If we were going to protonate something here, it would be the nitrogen first. If we're going to deprotonate something, it would be the oxygen first. Sulfur versus an OH. So, sulfur. So oxygen is more electronegative than sulfur, but because sulfur is bigger, we're introducing that third row of the periodic table now. A sulfide ion is more stable than a hydroxide ion. So the sulfur would be more acidic here. And how about here, red or blue?
Red, yeah.
Red. If we deprotonate the red proton, we have a negative charge adjacent to 2 pi bonds, so we can have resonance happening. If we deprotonate here, that's on the same carbon. We don't get any extra resonance if we do that, because we just went with a carbon with a lone pair that's localized. A carbon with a lone pair here is delocalized, and we can resonate all the way around. All right. In over a few minutes, we'll keep practicing with this, and then we'll start naming things and learning about alkanes on Thursday. We're doing all that stuff from the end of Gen Chem.